appreciate you all coming in tonight. And we have a small problem. We're not advancing. I am from Sioux Falls, South Dakota, which is the home of the EROS Center. We were placed there in the early 1970s in anticipation of a series of Earth resources satellites that were conceived of as a way of revolutionizing the monitoring of a changing Earth. Okay, we're moving. Okay, we'll start there. This is where we're working. This is where I am. This is a classic winter scene. Like you, I left Sioux Falls on Monday, and it was 50 degrees above zero, and that's a fabulous thing for us. What I'd really like to do today is to talk about a 40-year history of a program called Landsat. But before I get into any of the details about it, what I want to do is to provide a little bit of context of the idea of looking at the Earth from a distance. And we can go back to the days of the Greeks and consider this quote by Plato, in which he provides us the advice that we could rise above our current state on the Earth and look beyond to really understand what we have in the world we live in. And in fact, that's the concept behind a field of study called remote sensing. Remote sensing, in its simplest definition, is the acquisition of information about an object without physical contact. So, for example, we are all engaged in remote sensing. You looking at me and sizing me up. I'm doing the same, trying to figure out who's going to ask the questions that confuse me. And that's the process of collecting information without coming into that direct contact. In our case, in remote sensing, we have a tendency to rely upon the measurement of reflected or emitted electromagnetic energy. Our eyes, for example, see the visible portion of the spectrum, but with instruments we can look beyond what the eye can see and measure different wavelengths of reflected or emitted energy, and from that make up decisions about the characteristics of the features of the Earth. Now, this extra visual information that we have has some real advantages in trying to understand the characteristics of an area. Here's a pair of images taken by Landsat of the Raleigh-Durham area in North Carolina, and one is a false color image that combines invisible light, the near-infrared portion of the spectrum, with the red and green light that our eyes see, compared to one that's taking a different portion of the spectrum to replicate the green look of the landscape that we would normally see. Each one of these provides a little bit different information that when we look at the contrast between them, we can start to understand the meaning of features that we wouldn't see by just looking at limited dimensions of that portion of the spectrum. Now, when we are practicing remote sensing, we generally want to have a distant vantage point. And it started with the use of balloons, it evolved into airplanes, and now much of our work is done from the vantage point of space. And it's the space-based perspective that I want to talk about. What I'd like to emphasize is that all of this started with something called ERTS, the Earth Resources Technology Satellite, that was built by NASA starting in 1970 and launched in July 23rd, 1972, and that is what started this Earth observation era. Now, before I say too much more about ERTS, now called Landsat, I just want to give a little bit of history, and that history is the idea for looking at the Earth from the vantage point of space, primarily for the purposes of better understanding how our planet was changing and how we could use that information to better manage natural resources, was actually an idea that was first proposed by a man by the name of William T. Pecora, the director of the U.S. Geological Survey in the 1960s. Dr. Pecora, after looking at the growing use of space in the defense and intelligence world, realized that from the vantage point of space we could understand our natural resources in a way that could revolutionize the effective use of our lands. And so he, in concert with then Secretary of Interior, Stuart Udall, proposed something called Project EROS, which was this concept of using new technologies, new satellites to view the Earth and try to understand what its condition, how the planet's condition was and how it's changing. Ultimately, through a partnership with NASA, the USGS, and NASA moved forward with this program that is now called Landsat. We are approaching the 40th anniversary of this program. Since it was originally ushered into the modern era in July of 1972, we've seen 6 successful launches of satellites. One, Landsat 6, failed, didn't achieve orbit. We currently have 2 satellites, Landsat 5 and Landsat 7, that are still in orbit, although I can't say they're fully functional. And we are about a year out from launching the next in this series, the Landsat Data Continuity Mission, or Landsat 8, the name it'll be given upon launch, which is going to, we are planning on be launched in January of 2013. Now, over those 6 successful missions, we have had the most unique, comprehensive record of the condition of the Earth ever recorded. The Landsat series of satellites have imaged the Earth every 18 days, 16 days, or sometimes more frequently, to provide the potential for providing an image of almost every part of the Earth, except for the very high latitudes, that document the condition of the land. This is a permanent record, historic evidence of the condition of the Earth at given points in time since 1972. In the history of the human race, no other record as complete as this has ever been prepared for the surface of the Earth. So if we want to define or document the way things are changing and try to understand how it affects changes in weather or changes in economies, we have the record in order to do that. Now, when you study Landsat, you'll see all kinds of names of instruments like MSSs and TMs and ETM pluses. Those are all names given to the series of instruments flown by Landsat, going back to the original couple and then the newer ones in more recent missions. And those are the types of images that we get frequently from this series of orbiting satellites. Now, Landsat has a purpose, and its purpose is to provide an inventory of the global land surface, to measure changes, and to be able to attribute those changes to either natural causes or human activity. So Landsat was designed not to look at the ultimate in detail in the landscape, but to look at the patterns of the utilization of our natural resources at a scale where we can understand human activity from natural processes. And we need to do that seasonally, and we need to do that annually, and we need to do that continuously. And so in July, we will cross the 40-year threshold, the 40th anniversary of this pretty remarkable series of missions. Now, as I said, Landsat doesn't look at the ultimate detail. Our current satellites have a resolution of 30 meters. For those of you with an agricultural background, that's about 1/4 of an acre. So it's too small to look at what you're doing in your backyard, or too small to spy on your neighbor, or even to determine whether you got a new car or not. It's really enough to look at the condition of our agricultural lands, our forests, the growth of cities, and those types of things. On the left side of the slide, you'll see something called MODIS data. That's an example of a different type of imaging system that looks at the Earth on a daily basis, but not at that 30-meter resolution Landsat sees. And as you see, as we have a comparison of the two areas, there's a much different level of detail you have. One has a purpose of being very current, looking every day. The other allows you to look at the land at the scale that humans manage land. Now, there are many different types of sensors or missions out there measuring data. Some, will get down to measuring things as small as a meter, just a few feet. and others like our Landsat is at 30 meters. They all serve purposes. They're very complementary to each other. Seeing the ultimate in detail is not a practical or advantageous thing where you're trying to understand how the nation or the planet is changing. It's very good if you're trying to look at specific processes of urbanization, though. So all of these are parts of the arsenal of tools that people using remote sensing look at when they're trying to understand the processes underway on our planet. Now, every Landsat image is about 185 kilometers on a side. That translates to about 105, 110 miles. So we're looking regionally at things, and the vantage point of looking at things regionally is that we can see the relationship of the uses of the land to the underlying natural resources. We can see the proximities of our farms to our urban centers and the like, and really start understanding environmental relationships. The critical part is that our satellites right now orbit the Earth every 16 days, and so we're getting this regional look every 16 days potentially around the world, and it's been going on for many, many years. Now, over the 40 years of Landsat, the series of satellites have documented most of the major contemporary events that we have lived through or witnessed. And I just want to show a few examples of that. For example, many of us in this room probably remember the day we woke up to find out that Mount St. Helens erupted, which was in 1980. Here's a series of 4 images that were taken before or after the Mount St. Helens eruption. In 1973, we see the mountain and the protected forests. I should point out, in this particular slide, it's a false color image, and so the red indicates the healthy green vegetation, and that's one of the old traditions in remote sensing and understanding vegetation vigor. But anyway, so 1973 was pre-eruption. 1980 it erupted. Here in the 1983 image is what it looked like after the mountain blew out to the north, denuded the trees. That's what the grays and browns indicate. And then if we look at it in 1988 and 92, you see the return of the pinkish colors. That's the living, healthy vegetation regenerating in the ecosystem. And so this is a chance for us to see not only the destruction of a volcano, but the natural process of recovery that goes on. We can monitor glaciers around the world, and here's an interesting pair of images that show the gradual elimination of the snows of Kilimanjaro, made prominent by Ernest Hemingway's book. Because of this continuing monitoring, we can start understanding not only that we're losing glacial ice on this mountain and others, but we're able to understand how the land around the mountain is affected and start understanding what the connections are to the environmental changes that are occurring. You can certainly monitor, in the broad sense, the changing footprints of our urban areas. And here's Dallas-Fort Worth from the 70s to the 80s to the 2000s, in which the population doubled and the footprint of the city doubled as well. And of course, what were once 2 relatively distinct cities, Dallas and Fort Worth, are now one big, large megaplex. We've all heard about the changes in tropical forest, and in particular the loss of forests in the Amazon basin of Brazil. Here's an example of the types of processes that have been witnessed by Landsat, where on the one side is a 1984 image. Before much development occurred, there's a little bit of logging going on the far side of the image. But then in 2011, a few years after a very large dam was completed, we see not only the new reservoir that went into the image, but the white areas that are the losses of forest, of tropical forest that came about because of the settlement practices that are changing much of the rural areas of Brazil. Here's, I'm from South Dakota, it's my home, I always have to show a South Dakota image or two, and here's a series from 1984, 91, 2001, and so on to 2011. This is an area that's about 25 miles across and up in each of these images. In contrast to a lot of parts of the world, we are not in a drought cycle. We've been on about a 20-25 year wet cycle, and we have more water than we know what to do with in many parts of the state. This is an old Prairie Lakes region, and in 1984, about 15% of this area was covered with surface water. We're at about 40 to 45% now in 2011. And if you live in this area, you'll see roads flooded, new lakes formed, and a total transformation as our water bodies fill up. Now, if we look downstream to where I live in Sioux Falls, which is about 150 miles away, what we're seeing are runoff rates from our rivers that are greater than normal, and it's simply because the basin is saturated. And so runoff rates with any type of precipitation event are increasing. Now, there's a lot of ways to look at the value of Landsat, and here's just a couple of quotes that I think help us understand why the continuous observation of space makes some sense. In the first quote by a Russian that's responsible for a program called the Russian Transparent World Partnership, he concluded that by the continuous imaging of the space from things like Landsat, we are able to essentially democratize the events that are going on the surface of the planet and providing that unconcealable historic evidence that really allow all people to understand what really happened. The evidence doesn't go away. It's stored for perpetuity within the images. Another way of looking at it is from a colleague of many of ours, Curtis Woodcock from Boston University, in which he compares Landsat to the Earth's free press, and says that because of the global perspective that we've had since 1972, we have objective and undisputable evidence of the condition of this planet. That's the value of imaging the Earth on a continuous basis. Here's an example of one of the events that was witnessed by Landsat. Most of us probably have heard about the Chernobyl nuclear disaster that occurred in 1986. The first image in 1975, that's the area when the construction of the nuclear power plant was just being developed. If you look at the center image, you see the big blue blob, that's the nuclear power plant, the cooling pond for it, and the reactor was to the upper left-hand side of that. Around it, you see the dark greens, that's the patterns of agriculture, and the lighter greens, the patterns of forests, and the lighter greens and whites that are the agricultural fields. After the disaster, the area was contaminated, and through continuous monitoring of the region with Landsat, we've been able to look at how the land is recovering and being used. And essentially what we're seeing is that the agricultural lands are now in grasslands. They never did return to productive agricultural use because of the long-term contamination resulting from the explosion. Landsat wasn't designed for military purposes, but it certainly contributes to our collection of tools we use when we're trying to understand tactical and strategic responses to national security events. Here's an example of a series of images put together for Operation Desert Storm in the early 1990s, in which, in this particular case, in Kuwait, in the center image, you see a lot of dark cloud, these things, that's smoke coming from oil wells that were set afire by the Iraqis. And if you look at the final November 14th of 91 image, you see that the efforts to reduce, to eliminate the fires is having some success, and the smoke is going down. Afterward, this provided a means to really assess the environmental impact of what probably was a fairly significant environmental disaster. As important, these are maps of broad regions, and by looking at things regionally, we can look at pattern road changes that we wouldn't see if we were looking at very localized areas, and from that we can gain information we may need to start understanding what the movements of military troops are. And certainly one more example I want to emphasize, in 2010 when much of the country was struggling with how to respond to the Gulf oil spill, Landsat was one of many imaging systems enlisted to try to provide the intelligence we need to actively deal with this disaster. So, what drives the need for Landsat? It's used for science, It's used for operational activities, natural resource management. It's available to the public to understand their environment and the lands around them. No matter what our purpose is, we have the same needs. We need that global perspective. Our problems don't end at our borders, but we're affected by activities around the world. We need to look around the world with a long record of observation so we can understand how the things today had origins in decisions made 30 to 40 years ago. And we need to have all of this data in a calibrated, accurate form so that when you compare one image to another, the differences we see have meaning. They tell us something definitive about the condition of the land, the state of the vegetation, the quality of the water, or whatever other factor we're measuring. It helps us look at areas that we can't look at very conveniently any other way. And this is a part of a very innovative effort by NASA, the USGS, and the National Science Foundation, in which we use Landsat and other types of images to mosaic together the first image base of the Antarctic continent. And in this particular case, it provides us with a look that we cannot have from even standing in the ground in a particular area. We're seeing the region as a whole, and in fact, we can go beyond what looked like one big bunch of white stuff and display it in a three-dimensional form and start really understanding what the conditions of Antarctica are like. We can understand changes in ice, in flows, in depth, and other factors that are important in understanding how the Antarctic is responding to our changing world. It's become increasingly an important tool in understanding some of the factors that are pointed to as causes of our global climate change. And of course, one of the things we've heard much about over the years is that as we cut forests, particularly in tropical regions, that the increases of carbon in the atmosphere is contributing to warming. And so the use of Landsat to really understand the extent of that change is a pretty important and growing use. And here's an example put together by a colleague, Matt Hansen, at the University of Maryland, formerly South Dakota State University, but the trader left. The red areas are various densities of the amount of forest that were changed. Now, this was done not just with Landsat, but with other instruments. But because of the detail Landsat provides, we were allowed to very accurately statistically estimate the precise amounts of change between 2000 and 2005. And the interesting thing about this is that when you look at the continents with forest change, North America is higher than what we are seeing in South America. And that's counterintuitive if you follow what's reported in the press. And in fact, if you look at the countries with major amounts of change, U.S. is showing up pretty prominently in that box. And so, those are significant things to think about. We can look at it in more detail, though, and we've used this 40-year record to understand land change across the United States. This is a very generalized map that shows you the general rates of change for the different ecological regions of the country. And I think the one thing I want to point is that the redder it is, the more change there are. And if you throw in your geography, you'll understand that the forested areas are the areas that are changing the most in the United States. And it's not because we're eliminating a lot of trees for agricultural purposes, such as is occurring in Brazil, but we have an active commercial forestry sector that is planting trees and in some parts of the country able to harvest in 20 to 25-year cycles and then replant immediately after that. So our landscape changes rapidly, but it's very cyclic. Trees will be cut and trees will be replanted the next day. But when we look at it over the period of time, from the vantage point of Landsat, we're able to really measure the fact that over the last 30 years, we've had about a percentage or so loss of forest cover. So we are losing trees in the U.S., but not as alarming as that other study suggests. Now, many federal agencies make constant use of Landsat to understand the characteristics of our nation or to address their resource management challenges. The U.S. Geological Survey, for example, every 5 years puts together this map called the National Land Cover Database, which provides a map of the extent of croplands, forests, urban areas, and many other land uses or covers across the U.S., and it provides information on how those resources are changing, what the percent tree cover are, and how much of that surface is impermeable, how much of it has been paved over, a very important factor when we're trying to understand hydrologic processes. The Department of Agriculture, through the National Ag Statistics Service, on an annual basis, and one of the most aggressive uses of Landsat and other satellite imagery around, maps all of the croplands every season, and those are used to determine crop acreages across the country that ultimately help us understand yield potentials, market values, and many other very important economic variables. This is the 2010 cropland layer that was just released by the National Ag Statistics Service. We're doing similar kinds of things to map natural vegetation and translate those into fuel types that correspond to the ignition potential, the burn rates, the amount of energy that could be released of lands if they were to be set on fire. And this is really a critical tool to the nation's efforts to manage wildfires and to try to reduce the economic and human losses associated with fires, particularly those that occur in the wildland and urban interfaces. Fires is a major use of Landsat, and every major fire that occurs in this country is immediately mapped with Landsat, and it's monitored for years to follow as we try to understand recovery rates, we try to measure the effectiveness of the remediation that resource managers are using to reduce the erosion from the burned over area and other factors. And so Landsat on a daily basis gets put to use to try to improve the return to its condition of our wildlands. Now, in an example that I think is one of the more incredible ones, and one I'm a little nervous to talk about because the guy that did this is in the audience, Western water users have a problem. There's not enough water to meet the growing demands. The competition between urban uses and agricultural uses are increasingly in conflict. And so understanding how to best manage those scarce water resources is a real critical factor. Landsat has become, in recent years, the tool of choice to really help understand water utilization in the West and to help understand effective and inefficient water use, both effective and inefficient water use, and to adjudicate any disputes that are going on. And so through the translation of this thermal imagery, heat emitted measurements that Landsat collects, there's an ability to calculate evapotranspiration and ultimately translate that into terms relating to water use. Close enough, Rick? Yeah. Thanks. And we think that's pretty neat stuff, but so do others. The group that Rick and his colleagues that developed this, and Rick's with the University of Idaho, the Idaho Department of Water Resources has really been putting this to big use. Won an award from Harvard University's Ash Institute Innovation for American Government Award for finding an innovative technological solution that can very effectively improve water resources management. And it really is dependent upon Landsat. A lot of efforts have been made to quantify the value of Landsat. What are the benefits? What's the return on the investment that we have? And as the numbers you'll see here show, there's a pretty wide range, but the numbers are pretty big. In the case of a study done by the Western States Water Council, in extrapolating the value of what Idaho is doing with water across the West, the estimate is that there's a potential savings of $100 million a year in improved water resource management from the use of Landsat. The American Society for Photogrammetry and Remote Sensing, the largest geospatial and remote sensing organization in this country, estimated just under $1 billion a year of benefits, and in a recent study conducted by the company Booz Allen, they're estimating it's close, perhaps as large as $7.5 billion. Pick a number, they're all big. The thing is that Landsat does contribute to addressing societal needs on a daily basis. Okay, I want to talk a little bit about where we are today with Landsat. I said at the beginning, Landsat started in 1972, and we've been providing images for a long, long time. But the fact of life is that we've been selling images for a long, long time, because that was the government policy that we operated under. For the most part of the Landsat record, we sold images for the cost of reproduction, which at its low point was $200 an image. That's for 110 by 110 miles worth of imagery. That's a lot of money. And at its high point, it was over $4,000. As you can imagine, that's a lot of money, particularly for agricultural and natural resources, forestry types of applications. And so in October of 2008, the USGS made a bold decision, and that's to make the entire Landsat archive, which, by the way, right now is more than 3 million images of the Earth, going back to 1972, and we made those data available to anybody, period, at no cost. And this has started a revolution in the use of Landsat data that we had hoped would happen, but it's occurring at a rate that we just simply didn't expect. Here's a chart that shows how the data are flowing out of our facility in Sioux Falls, South Dakota. Let me start with a little history. When we were selling data, our best sales year ever was the early 2000s, and we distributed around 21,000 images. That's a good number. The first year we made Landsat data free, we distributed about 1 million. And now we're at about 3 million. The rates are growing, and we're sending a lot of data out. We're sending those data to over 180 countries. And we're using more imagery in our archive than we've ever used before. About 2008, before we made all data free, our estimate is of our archive of Landsat 7 data, that's imagery from 1999 to the present, users purchased 7.7% of this collection of imagery from around the world. Now that we have a free data policy, the numbers are up to about 65%. And in fact, if we just look at the images that are not completely cloudy, it's closer to about 80%. So it's a big number. So all of a sudden, this investment that the American taxpayers have made is now being distributed far and wide and being put to use for peaceful uses to try to understand and better manage our natural resources. Now, just a quick footnote, if anybody in here is interested in looking for Landsat imagery, they're available on the web. Here are 2 websites, and I believe these are on some of the handouts that were at the back of the room. But you can go query our archive, look at the coverage from 1972 to the present. If you see something you like, you can download it, either in a very large format that's for scientific and applications uses, or in JPEG forms that you can look at in full-blown resolution to really see what's going on. But available to anybody through this site, and it's at no charge. Okay, now at the beginning I said we have 2 satellites still in orbit. I'll just tell you a little bit about where those satellites are. Landsat 7 is our most recent satellite, and it was launched in 1999, and so that means it's actually now in its 13th year, so it's old. This was a satellite, by the way, designed with an expected life expectancy of about 5 years, and so we're getting very noble service. It's collecting over 350 to 400 images of the various parts of the globe every single day. Those images are available, but it has a small problem, and that is in 2003 there was a mechanical failure on board the satellite that means that 22% of all of the information in every image is dropped. And here's what it looks like if we're looking at the greater Washington, D.C. area. From about a little less than the center of the image radiating out, you'll see these data gaps, this Venetian blind effect where there's a loss of imagery. These data still have terrific scientific value. They still help us understand a changing Earth, but for some uses the data are compromised. But it's the best we have, and we continue to collect it and make very, very practical use. In case you're trying to figure out where we are, there's the Dulles Airport area, the D.C. area, so we're somewhere around here. Probably, I hope we're not in one of the gaps. probably one of the more amazing stories in the history of Landsat is a satellite called Landsat 5, which was launched in 1984. It's 27 years old. It was designed to last 3 years, and it's still in orbit. Now, it's not all good news. In November of 2011, it had a mechanical problem, electronic failure, an electronic problem that has caused us to turn off the imaging and to do an investigation of whether or not we can correct the problem. And so the flight engineers responsible for Landsat 5 have been investigating ways to return this to service. Our hope is to turn it back on by May in time to image the northern hemisphere growing season. It's very important for agricultural purposes. Or we may switch to an old instrument that was turned off in the late 90s called the multispectral scanner system. It's not as good as the thematic mapper, the one we rely on. It has much better resolution and just a higher quality image. But it might be some way to continue to provide life for this. But it's all up in the air. For now, we've got one satellite flying. The good news, and it's great news, is that the next Landsat is getting ready. Through a partnership between NASA and the U.S. Geological Survey, a mission called the Landsat Data Continuity Mission, LDCM, is being built. NASA is responsible for all of the complicated space stuff, and the USGS is building the ground system, and will take over operations after it's placed into orbit and checked out. And it's going to continue this record of providing seasonal coverage year after year of the globe. It's going to be done in a way that's consistent with all of the other Landsats, so the imagery we acquire next year from Landsat 8, what LDCM will be called, will be comparable to all the other data in the archive. And so it continues this long record, and while it's designed for a 5-year life with consumables, fuel that may let it last for perhaps 10 years, that may mean that 10 years from now we're talking about a 50-year record, which is still the longest continuous record of the Earth ever collected. Now, LDCM is going to have some new stuff on it, better spectral imaging capabilities than we've ever had, and there's a bunch of jargony stuff in there that doesn't mean much to most of us. The key is we will have better data, and we will hopefully start having it in early next year. And just to provide some evidence that I'm not making any of this up, here's some images of the two primary instruments, the operational land imager and a thermal infrared sensor, and the spacecraft that those instruments are being attached to that will be then put upon a rocket and sent into space in January of next year. So that's Landsat 8, and that will get us to 2018, maybe longer. That means it's time to start thinking about Landsat 9. The development of space systems, of satellites, takes a long time. The estimates are 5 to 6 to 7 years from conception to launch, and so we have to start now. Through a series of decisions made in the federal government, some by the starting with the Office of the President, the National Space Policy came out that placed a strong commitment on land observations, land remote sensing, Earth imaging, and said that the USGS director with NASA will work together in maintaining a program for operational land remote sensing observations. The President, in his budget submitted for 2012, followed up by that by suggesting not only do we start looking at the development of Landsat 9 and 10, but that the program would be moved to the USGS, the Department of Interior, part of the U.S. Geological Survey, for permanent operational use. And so Bill Pecora proposed the idea of Landsat, Project EROS, in 1966, and in 2012 the recommendation was return it to the USGS to continue on with it. Now, if this happens, it will be done through the same close partnership with NASA that there always is. They design spacecrafts, instruments, and their expertise is unmatched. But the budgetary and management home of it would be shifted to this agency. Now, as we all know, it was a tough budget year. We were not left out in the cold, but we have a small amount of planning money to begin making decisions in advance of building Landsat 9. And so the future continues. So let's just wrap up by thinking about a few things. Let's start by realizing that the planet was different 40 years ago. There were less than 4 million people on Earth, and that equates to 9.4 acres of land per person on the planet, okay? But the world is shrinking, and of course Landsat, that is one of those standards that are used around the world to understand how it's shrinking, has been measuring it constantly since then. The data from Landsat are being used to address many societal issues on a daily basis. When Landsat 7 was launched, that continues this record, it was looking at 6 billion people, a growth of 2 billion people over the 27-year period. In 2013, when we launched LDCM, we're over 7 billion people, but we still have free Landsat data now to look at the changing Earth and to understand how our decisions are changing the planet and how we maybe better manage it so that we're not leaving it in a condition that's unsuitable for the next generation. And when we get to the end of life, we'll be at 7.5 billion people. And because of this continuing growth of the human race, the shrinking planet that's afforded by our needs, this ability to use the perspective of space is really a pretty critical thing. So if we're looking at natural resources management, we really need to have an investment in the tools that are needed to allow us to understand how the planet's changing and make wise decisions. And our hope is that the Landsat legacy will continue and will help build on the wise decisions that make effective use of our planet's resources. I want to just close by referencing a quote that was just published a couple of weeks ago by Robert Kennedy from Oregon State University, in which in his article reflecting on how we're using remote sensing to understand the Earth, concluded that as the longest running continuous satellite imaging data set for land processes, Landsat data provide unparalleled witness to the enormous changes occurring on the Earth since 1972. And 3 million plus images in the archive are the evidence that proves that. And so with that, I want to thank you for paying attention. And if I can answer any questions, I'd sure be happy to.